Hello friends and welcome back. The topic of this video is the simple pendulum, which is one of the most famous and interesting or most used applications of simple harmonic motion, and that you've already seen in PHY1001 or PHY1002 a few months ago. So you attached, a mass onto, a pivot, mass m with a string of length L to a pivot, and then you watched it go back and forth, and you measure the gravity constant from your experiment. But let's see again. So you may have your lab script with details about these calculations already, but let's just go over the calculations again. What is, now that we're studying mechanics, how does one interpret this scenario with mechanics and what you already know and what you're learning now? Well, there's definitely a weight that is pulling this mass down. And then, given that now we love polar coordinates, it might seem like a natural thing to do to split it into the radial direction and the angular tangential direction, right? If we call this the angle phi, okay? And so what does F equals ma look like in this context? Well, these are the components of the force of gravity, and inevitably there's going to be some tension. I hope you remember about tension in the string. So in the radial component, I simply have, so if I use Newton's second law, in the radial component, I have, I forgot the dots, whatever. In the radial component, I have t, and this is again phi, mg cos phi cancelling out. And so the overall acceleration in that direction is zero, because the string is not stretching and it's not compressing. However, and this is the important bit, there's a restoring force. There's a component of the gravitational force in the phi direction, which is actually minus, look, mg sine of phi. All right. So removing this m cancelling out or simplifying, what I'm left with is so that the acceleration in the phi direction is minus g sine of phi. Now we're almost ready, but we need to do a couple transformations here. Step one is realizing that the acceleration in the phi direction is simply the length of the string times the angular acceleration. You may remember that the displacement along an arc, a little displacement is simply the length of the arc times delta phi. This is if you travel a small distance along a circumference, then, and this is delta phi, then this delta x is equal to r delta phi. And in my case, r is simply the L. I called it L. So acceleration would be the second time derivative of L phi, with L not changing because the length of the string, the pendulum, is always the same. This is just L phi double dot. So that's simplification number one. Simplification number two is if you take small angles, and with small angles, important, we mean that I can make the approximation where theta is roughly the same as the sine, not theta, sorry, phi, is roughly the same as sine of phi. And you can check numerically when this is true, but for small angles, for sure this is true. Then, let me zoom out a little bit. Then this equation, which was none other than F equals ma, I can actually rewrite it in the more interesting form. Actually, let me rewrite it here as L phi double dot is equal to minus G phi. Or, okay, no, that's it. Now, this reminds us a little bit of the same structure of the simple harmonic oscillator with some phi double dot. We used to have, so what we used to have in simple harmonic motion, we had x double dot is equal to minus omega squared x. Here we have L phi double dot, which actually I'm not too happy with this yellow circle around my phi, so I'll just rewrite it. L phi double dot is minus G phi. So let me just rewrite it as minus G over L phi. And you know where this is going. We can take this quantity, actually, we can take this quantity and we call it omega squared. And lo and behold, we have exactly the same solutions as we've seen for simple harmonic motion, the circular, uniform circular motion. Okay, I'm taking way too long to do this. I need a select all button somewhere. And so the bottom line is that the solutions for the motion of a pendulum for small angles, important, is that the angle phi is equal to some amplitude times cosine of omega t plus, yeah, maybe that's why typically we use a different name for, well, plus some, let's do it with this symbol, plus a phase, where this frequency, angular frequency of the pendulum is the square root of G over L. In most textbooks, I think you would find this phi here expressed as theta. It's just a different name, so it doesn't really tell us anything different. And yeah, there's a lot of interesting physics that one can study with this. Interestingly, the first thing that's very interesting, that I find very interesting, is this expression. Look at what this is telling us. So the angular frequency of a pendulum is proportional to the square root of g. So the stronger the gravitational acceleration, the bigger the angular frequency, which in turn results in a shorter period, because period and angular frequency are have an inverse proportionality between them. And so there's several things to notice. One, the stronger the gravitational attraction, acceleration, the shorter the period. And this is probably understandable. If you go on the moon where there's less gravity, then the same pendulum would swing more slowly. The longer the pendulum, the longer the oscillation as well. And this is probably not surprising. If you take, if you swing a small 10 centimeter pendulum, then the period is very quick. If you get a 10 meter Foucault pendulum, then you can see that it takes a much, much longer time. And lastly, that this period is independent of both the initial angle, which is not quite the same as the phase. Hey, so this is phi at t equals 0. So the initial displacement, let's write it like that, of initial displacement, angular displacement, and it's independent of the mass, which is probably a little bit surprising, because you might guess that if you attach, you know, a bigger mass at the end of a pendulum, that gravity pulls stronger and more strongly, and so you have a shorter period, for example. But actually, because of Newton's second law, where yes, the force is bigger, but the force it takes to accelerate is also proportionally bigger, the pendulum has the same exact period for any object, given the same planet, same gravity, and given the same length of the pendulum. Very, very interesting. All right, then thank you so much for watching, and see you soon.